So, good evening again, my friends. I want to welcome you again to our webinar under the title of the Naughty Oil Droplet short PVT story that will be delivered by Engineer Muhammad Amin. Before starting, my friend Omar will be conducting a small presentation, then Engineer Muhammad will conduct the technical session. So, Omar, the stage is yours now.
Thank you, Jad. Good evening, everyone. So I will give a small presentation about OPA July and August courses plan. I'm Omar Hamid, business developer at OPA. So the first offer that we have is on the recorded courses. So as you can see, the courses on the left side and the prices next to them is the price before the discount. I will tell you the price after the discount on the next slide. So for each of these courses, there is 15 hours of recording, and there's exercises and assignments. So you solve these exercises and assignments, and after watching the recordings, and you get the support from instructors when you have any questions. And of course, at the end, when you submit the exercises and assignments, you will get a certificate of completion in the course that you're taking. So this is the table for the discounts. So the more courses you take, the more discount rate you get. And as you can see, for one course, it starts by 15% and it reaches 50% if you take 7+ courses. So if you're interested to join one or more of these courses, recorded courses, you can scan this QR code, or you can fill in the link that will be sent right now in the chat. And also you can contact us on our social media and register from there after the webinar if you want. So just a few seconds, if someone wants to register now, I will give you some time. Okay, and second is the PVT analysis course, which is a live course for 3 weeks, starting from 14th of August. The original price of this course is $300, and there is right now an early bird offer, 30% off, so you can register for $209.99. Here it says that the early bird will finish on 9th of July, but we decided to extend it for a few more days to give you a chance to register after this webinar. So you can register right now for the early bird price. So hurry up before it finishes. So what are the criteria of this course? So it will be 2 weeks of course and theory, then there is a 1-week project. It will be between 35 and 40 hours of live training. In the course, you will have 3 hours per day for 10 days, and the project days are 1 of 2 or 2 hours per day for the 5 days. There will be really case studies and data that you'll be working on, and the full support from the instructor to answer all your questions inside and outside the sessions. And of course, you'll get a certificate of completion at the end of the course that will strengthen your CV and that will show that you're an expert in the PVT analysis. So you can also scan this QR code or fill in the link that will be sent to the chat. So if someone wants to register, I will give you also 10 seconds. Okay, and how to become an OPA ambassador? It's very simple. You just take one course with us, whether it's a recorded course or a live course, and you join our OPA ambassadors community. So in this community, you will get lots of benefits. You will get discounts on the course, all the courses in the future. And also you will get group discounts when you get your friends with you. So join our happy ambassadors to benefit from this. And at the end, I would like to inform you about our upcoming service, which is called 4x4. So this program is a focused, fast, and effective knowledge program. It's composed of 4 times 1 hour long consecutive sessions. So it will take place for 4 consecutive days. For each day, it's only 1 hour. And it's delivered by highly experienced instructors. And the price for each group of 4 sessions is $4.44 only. We will announce the first program very soon on our social media. It will be about drilling fluids, so stay tuned and be ready to register from our social media when we announce about it. And at the end, the rules for this webinar, so please keep your microphone muted and the camera closed. Put your questions in the chat box and they will be answered at the end of the session by the instructor. Use your full name as written in the registration form in order to be able to take the attendance for you. And note that the certificates will be sent within 1 week from today. So don't worry if it takes some time. We did not forget you. We are just preparing them. And thank you a lot for paying attention to my presentation. Now back to Jad.
Okay, thank you, Omar. So before Engineer Muhammad presentation, I would like to introduce Engineer Muhammad to you. Engineer Muhammad is a senior reservoir engineer at General Petroleum Company, JPC, Egypt. He has more than 6 years of experience in asset evaluation, reservoir characterization, and simulation. He participated in many and recently managed many successful field development plans in green and brownfield within the offshore GOS area. Engineer Muhammad has a correlation that holds his name in the field of reservoir fluid flow modeling. He has a bachelor and master's degrees in petroleum engineering from Zwaz University in Egypt, and also has many publications in several journals and conferences, like NPM, IJRTE, and many others. So, thank you, and now Engineer Muhammad, the stage is yours.
Okay, thanks, Jed. Welcome, everybody. Our session today was titled "The Naughty Oil Droplet." We will speak about the problems of the oil production. These topics of our today's session, we will introduce the production system. Also, we will talk about the flow assurance definition, the flow assurance studies strategy, how to make a flow assurance study. Also, how to make compositional analysis for the hydrocarbon from the view of the flow assurance study, how to use your PVT data to characterize and get a solution for the flow assurance problems, and finally, we will introduce a case study. First, the production system has many components, beginning from the reservoir, then the connection to the surface with our well, then the flow will be coming from the reservoir, then the tubing, then the wellhead, flow lines, and separator, and finally into the stock tank. Through the journey of the reservoir fluid, many hydrocarbon components will be deposited into the production system, like the asphaltene or the wax or the scale, and many other components will be deposited into this production system. So these fluids or these solids will be deposited into can be deposited into the reservoir, so it will restrict the production of the well and influence of the productivity of the well. Also, the near wellbore region, so it will reduce the production of the well. Also, it can plug the perforations. And through the journey to the surface, some deposited will be formed into the tubing, so it will restrict the production. And finally, many of these solids will be deposited into the production facilities. The studies that are concerned with this deposition type is called flow assurance studies. The flow assurance, is meaning that this is a study that will evaluate the effects of fluid hydrocarbon solids like asphaltene, wax, and hydrate, scale, and other solids. And it will study the effect of deposition of these solids on the production. And how can we prevent and screen these problems and prevent these problems to occur before having it into our production or affect it on our production. These problems like asphaltene deposition, wax deposition, hydrate formation, corrosion, emulsion, and slugging. All these problems concerned with the hydrocarbon phase of our reservoir fluid. But we can also have a deposition of inorganic solids like the scale. The scale that is formed when blending the water from the surface, like in water injection process, and the formation mode. The strategy for flow assurance studies has four main steps. The first step is fluid sampling. The second is how to characterize the composition of reservoir fluid. Third, how to screen the problems that can occur due to the reservoir fluid. And finally, after having or detecting that we will have a problem into the future, how to make some experimental work to further screen and further analyze this phenomenon. First, for fluid assembling and the transport, we should assure that the sample that we will take from the reservoir should be representative to the original reservoir fluid. By taking into consideration that no leaking will be occurred from the after sampling and until its delivery to the laboratory. Also, in some cases, when we have H2S and CO2, we should use sample bottles that resistant to the H2S and other corrosive components. Because if we don't use this type of sample bottles, the H2S and the CO2 will react with the metal of the sample bottle, and finally the composition of the fluid that into this sample bottle won't be representative to the reservoir fluid. It will underestimate the corrosion effect of the reservoir fluid. Also, if we are studying the asphaltene deposition, a certain type of bottom hole sampling bottles called single phase MDT bottles should be used because it will conserve the reservoir fluid without any deposition for the asphaltene or wax or any other hydrocarbon solid. The second step into the strategy for flow assurance studies is that we should characterize the composition of the reservoir fluid. As we know, the first step into the reservoir fluid composition and characterization is to making a flash test. This flash test will indicate the component mole percent for the reservoir fluid. But for the flow assurance studies, we are not concerned by each component. We are concerned by each group of this composition of the reservoir fluid. which is made by an analysis called SARA analysis. The SARA analysis simply type or divide the reservoir fluid composition into main 4 groups. The first group, referring to S, is the saturate fraction of the reservoir fluid. The saturate fraction is the group of components that has no any charge. It is non-polar. Also, its bonds are saturated bonds. So the bonds between the hydrocarbon or the carbon and the hydrogen are saturated bonds. Okay. The second component for the reservoir fluid is the aromatics. Aromatics has 1 or more aromatic rings, and also it is more polar than the saturate. The third component for the reservoir composition is the resins. The resins has more polar charges, and also it will be solved into the heptane. It will be solved into the heptane. The final group of the reservoir composition are the asphaltenes. Asphaltenes also has some polar action, but it is insoluble into the heptane. So the difference between the resins and the asphaltene, it is for the solubility into the heptane. The SARA analysis is very, very important for identifying oil that will have asphaltene problems. This plot showing the method for applying the SARA analysis. The SARA analysis, we will begin by the crude oil sample, then we will add some hexane. So the asphaltenes will be deposited. Then adding more hexane, the other 3 groups will be deposited. The resins will be deposited by using or by adding the trichloromethane. Then adding more hexane, the aromatics will be deposited, and finally the saturates will be into the solution. An example for the SARA analysis here, we have the saturate percent, weight percent, the aromatics, resins, asphaltenes, and wax. So the third step into the flow assurance study is to inspect the common or the possible problems that may occur due to some compositional existence into the reservoir fluid. Okay. We will focus on 3 common problems that are asphaltene, waxes, and gas hydrates. So first, we will introduce some simple methods that by using it, we can know if this crude oil will have some problems like asphaltene deposition, wax deposition, or gas hydrate formation. And if this screening criteria results in possibility of having some problems, we will do some experimental work to further analyze this problem. For the asphaltene is the component of the reservoir fluid. It is the compositional group of the reservoir fluid that is soluble into the toluene, some aromatic solvents like toluene, and any other aromatic solvents. But It is precipitated. It is precipitated when adding some saturates like the hexane or the pentane. Okay, so the golden rule for the asphaltene deposition is that if we add some saturates, some light components like the hexane to the main reservoir fluid, so the asphaltene will deposit. The asphaltene will deposit. By using the golden rule, we can guide some problems. Like we have a case study that we open two perforation into an oil well. One perforation is producing light oil, and the other is producing a heavy oil, So the heavy oil have some asphaltene, into its composition, and the light oil have the most composition into the light oil are the light saturate components. So when we open the two perforations, the two oils are met together. So the asphaltene deposited due to adding the light saturate components from the light oil to the heavy oil. So by this interpretation, we were guided that we should isolate the heavy oil interval from the light oil interval. Again, the high asphaltene content doesn't necessarily mean that we will have a problem of asphaltene, because by using the rule of that the asphaltene will deposit only when we add light saturate components. Okay, so the amount of asphaltene that is existing into the fluid is not the criteria that we are searching for, but we are searching for the equilibrium between the asphaltene and the other components. Okay, we have some example like the Venezuela oil. The Venezuela oil is very heavy, containing about 17% of asphaltene. However, it has no asphaltene problems. Despite the Algerian crude oil that is very light, and to contain low percent of asphaltene, despite that, it will have some difficulties into the production due to asphaltene deposition. Why? Because the light oil have more components that is light and saturates that are responsible for the deposition for the asphaltene. So the instability of the asphaltene caused by, first, the temperature or the pressure changes into the primary depletion. If we have some changes into the temperature or the pressure during the production, it can have some effect on the asphaltene stability into the reservoir fluid. Also, the fluid blending, as in our case of opening two intervals of heavy oil and light oil. This fluid blending can also be a source for the asphaltene deposition. Also, the gas injection. Gas injection means that we are adding some light saturate components to our fluid. So this saturate light components will deposit, can be responsible for the asphaltene deposition. So it's coming to the question, how to know if the crude oil will have asphaltene deposition problems? First, we have some criteria that were noted by the deep water engineer. Like, if we have a crude oil that is light with low compositional molar of C7 plus. Also, if we have high bubble point. Also, if we have a high difference between the initial reservoir pressure and the bubble point pressure. Finally, if we have a high oil compressibility factor. If we have a high oil compressibility factor. As we can see, all these phenomena are seen into the light oil, not the heavy oil. The deep water plot, on the x-axis, we have the density for the reservoir fluid at the reservoir pressure, and on the y-axis, the difference between the initial reservoir pressure and the bubble point. We have three regions. The first region, if we have a point that is located here, so it means that we will have severe asphaltene deposition problems. If we have a point that existing here, that is mean that we won't have any problem concerning to the asphaltene deposition. If we have a point that existing into this region, it means that we have a possibility for asphaltene deposition, and we are in need for other analysis that can direct us or some experiments to do further analysis for the asphaltene problem. The second screening method is using from the SARA analysis results the weight percent of asphaltene versus the resins. If we are plotting the resins into the x-axis and asphaltene on the y-axis, if the point or the intersection is located here, that means that we have an unstable asphaltene deposition. If our point is located into this region, that means that we will have a stable or no problem associated to the asphaltene. The third method is using the colloidal instability index. The colloidal instability index equal to the saturates percent from the SARA analysis plus the asphaltene from the SARA analysis, then over the aromatics plus the resins. If we have a colloidal instability index that is below to 0.7, that means that we have a stable environment for the asphaltene deposition. If this factor is above 0.9, that means that we have an unstable environment for the asphaltene deposition. Also, we have a graphical representation for the colloidal instability index. We have three regions for severe problems and no problems and possible problems. Finally, this method was introduced by Schlumberger. It is about the difference between the oil density at the initial reservoir pressure and the oil density at the bubble point in gram per cubic centimeter. If the difference is more than 0.025, so this system is unstable for the asphaltene deposition, and we will have some problems associated to the asphaltene deposition. If the difference is less than 0.02225, so we won't have any problems due to asphaltene. These are two examples for two oil samples. The first, having no problems for the asphaltene deposition, and the other one have severe problems due to asphaltenes. We can note that for the crude that have no problems due to asphaltene, the C7 plus molecular percent is higher than 59. But for the crude that have problems due to asphaltene, the C7 plus has less than 46 mole percent. Also, we can note that the asphaltene percent is more than 3 into the crude that having no problem, and it is less than 0.5% into the crude that will have severe problems. Okay, so again, the criteria for the asphaltene deposition is not the amount of asphaltene. It is about the equilibrium between the asphaltene and the other three groups from the SARA analysis. Also, we can note that the bubble point, the difference between the bubble point and the reservoir pressure, the bubble point here into the oil that have problems due to asphaltene is very high compared to the oil with no problems. Also, the reservoir pressure, we can note that it is higher into the crude with no problems. Also, for the compressibility is higher into the crudes that will have some problems due to asphaltene. For the experiments due to or to further analysis asphaltene deposition, and also all the experimental measurements for asphaltene or wax or gas hydrate are about that we are manipulating or changing the pressure and temperature. They monitor the asphaltene deposition or wax deposition or the gas hydrate formation. Then we are drawing finally a curve. This curve is formed from many points that representing a combination of pressure and temperature. If we exceeding this curve, that means that we will have a problem due to asphaltene or wax or hydrate. So this curve is called the asphaltene deposit envelope. To have no asphaltene problems, we should be far from this curve. Okay, so from this plot, we can see that we will have some problems due to asphaltene and also wax and the hydrate. For waxes, we mentioned that the waxes are saturated organic components. The main factor that controlling the wax deposition, it is about the temperature. Also, the pressure and composition effect on wax deposition, but not greatly as the temperature change. So the beginning of wax crystallization or deposition or forming, it is about the temperature. It is about the temperature. It's called the wax appearance temperature. The wax appearance temperature. Again, the question is, how can I know that this crude oil will have some problems due to wax deposition? If we have a stock tank oil sample and we measure the wax content, if we have a wax content that's greater than 2% and our production system temperature is normally about or we have a wax appearance temperature that is more than 120 Fahrenheit, that indicates that we will have a wax deposition. So if we have the wax content more than 2% and we have wax appearance temperature that more than 120 Fahrenheit, that can indicate that we will have a wax problem. For the wax appearance temperature, if we want to specify the conditions for the wax appearance or the wax deposition, we can measure two properties. The first is the wax appearance temperature, and the other one is the pour point temperature. The wax appearance temperature is the temperature that small amount or the first forming of wax crystals are appearing into the solution of the reservoir fluid. The second one is the pour point temperature. The pour point temperature is the temperature at which the oil will be gel-like. The oil will be like a jelly. Okay, so if we have the system temperature, the production system temperature is more than the wax appearance temperature, so we can say that we won't have any risk due to wax deposition. If we have the system temperature is less than the pour point, the system temperature is less than the pour point, that can indicate that we will have a severe wax problem. But if we have the system temperature that is between the pour point and the wax appearance temperature, so we can say that we have a neutral of possible wax problem. Finally, the gas hydrates. The gas hydrates formed when contact occur between some gases components like methane, ethane, propane, and carbon dioxide and hydrogen sulfide and the liquid water. But this contact occurs at low temperature from 0 to 40 Celsius and high pressure conditions. This is the shape for gas hydrate. It is ice-like. The crystals of water will grasp some components, the components of methane, ethane, into between its crystals. So it will form like this acid, this ice. But we have a criteria to form the gas hydrate, that the system has a temperature that is less than a certain temperature called hydrate temperature. So the hydrate temperature is the temperature at which the gas hydrate formed when contact between some gas components and the free water. How we know that we will have a gas hydrate formation problem? We have a curve. We have a curve according to the gravity for the gas, according to the gravity of the gas and the system pressure So if we assume that we have a system temperature, a system pressure of 1000 psi, then also we have a gas that has 0.8 gas gravity. So we can go horizontally until meeting the gas gravity curve for 0.10 for air, then go vertically to meet or to know the hydrate temperature. We have a case study here. We have a sample that was taken from an oil well from the north of Texas, and we made a complete lab work to assess the risk for the flow assurance problems like asphaltene and gas hydrate. We have the reservoir pressure, the reservoir temperature, the DOR, the bubble point. We can notice that the difference between the reservoir pressure and bubble point is not very high, so we can expect that we won't have a problems due to asphaltene. Also, we have the density from the stock tank oil, the density for the reservoir fluid at the bubble point pressure, the density of reservoir fluid at initial reservoir pressure, the contamination into the stock tank oil and the reservoir fluid. First, also we have the compositional analysis. As we knew from the representation that we are searching in the compositional analysis for the C7 plus, the C7 plus, okay? So we have a low C7 plus, okay? So we made a thorough analysis for this oil, so we can group these components into 4 groups for saturates, aromatics, resins, and asphaltene, and also further analysis for wax determination. First, we use the first screening method of Dubois plot. We have the initial reservoir pressure, the bubble point pressure. We calculated the difference between the initial reservoir pressure and bubble point, and also we have the reservoir fluid at the initial reservoir pressure. So first, horizontally, we have the reservoir fluid density. It is about 0.8. It's like here. And vertically, we have the difference about 1000. So the intersection is here. So we have the intersection into the minor or no problems due to asphaltene deposition. Okay. To confirm our result, we can have the asphaltene versus the resin from the thorough analysis. Okay. So horizontally, the resin is about 18, and the asphaltene percent is less than 1%. So we have here, we have this point into the stable area. So we can expect that we won't have any problems due to asphaltene. Then the third method for screening for asphaltene depositional problems is using the colloidal instability index. The colloidal instability index is the ratio between the summation of saturates plus asphaltene and aromatics plus resins. We have the thorough analysis here. We calculated the colloidal instability index. Again, if we have a colloidal instability index that is more than 0.9, so we can expect that we will have a problems due to asphaltene. If we have the colloidal instability index that is less than 0.7, so we can expect that we won't have any problems due to asphaltene deposition. But according to our result, we have unstable condition for asphaltene deposition. Okay. So from the previous two methods, we have no problems due to asphaltene, but the colloidal instability index calculate or determine that we will have a problems due to asphaltene deposition. Okay. So we will go for the fourth screening criteria. It is about the density difference. We have the density at the initial reservoir pressure and the oil density at the bubble point. We have the difference. Okay. So the rule for the density difference is that if we have a density that is more than 0.025, so we will have unstable environment for asphaltene deposition. But if the difference is less than 0.025, so we will have a stable environment for the asphaltene deposition, as in the case here. So we have a stable environment for asphaltene deposition. So from the four screening criteria, we have three of them indicate that we won't have any problems due to asphaltene deposition, and only one screening criteria indicate that we will have a problem due to asphaltene deposition. So we can say that we won't, it is very low possibility that we will have asphaltene problems. For gas hydrate also in this sheet, if we have a system that is operating at 1,500 psi and the gas gravity is about 0.7, so the hydrate formation temperature is about 68. So 68. So if the system is operated on a temperature less than 68, so we can expect that we will have a hydrate formation if we have any free water production. So at this point, we come to the end of our session today, and it's time for questions.
Thank you so much, Engineer Muhammad.
Thank
So
you.
please, anyone have anything, any question, please make sure to type in the chat and I will read it for you, Engineer Muhammad. And this time also, please, I will share with you in the chat the feedback form. Please all make sure to fill it so we can always fulfill your needs. I got some questions. So we have a question about okay. Define the flow assurance.
The flow assurance is the kind of study that is concerned about the deposits that restriction the flow. That is restriction the flow. Why this restriction is occurring? Due to the deposition of some solids. some solids coming from the hydrocarbon phase, like the asphaltene, the wax, and the gas hydrate, the any other, and some deposit due to the interaction between the formation water and the injected water, like the scale. Okay.
Okay, we have another question. Gas hydrates can be in oil or in gas wells and systems.
Okay, it is most common into the gas production. It is common into the gas wells that's producing only gas. But if we have a huge gas production, like if we have an oil well that has a great amount of production gas, so we can expect that we can have some gas hydrate formation problems, especially into the surface facilities.
Okay, some students are asking about this webinar, so don't worry, this webinar will be uploaded on our YouTube channel, and you can visit and watch this webinar again and the presentation also on YouTube whenever you want. So if please anyone still have any question, don't hesitate to type it. Okay, we have a question. Does asphaltene reservoir itself prevent flow in the initial phase?
What? Again, please.
Okay, if there is asphaltene in the reservoir, does it prevent the flow inside the reservoir?
Yes, if the asphaltene is deposited into the reservoir, it will restrict the oil production. Okay, so why the asphaltene is deposited into the reservoir? Due to injection some light saturate components, like in the case of gas injection. Okay.
Okay, we have another question. That is, if you can please explain more about how adding light components destabilize asphaltene, like mixing other oils with asphaltene.
Okay, so when we add some light components to a solution that have asphaltene, it will uncover the resin protective layer covers the asphaltene molecules. So some colloidal action will occur between the asphaltene molecules that will lead to aggregation between the asphaltene molecules until reaching to a critical mass. So the asphaltene in this case will be deposited.
Okay. Which tools we use for test the presence of asphaltene or others in the well?
Use for what?
What tool do we use to test for the presence of asphaltene? How do we know that there's asphaltene in a well?
How do we know that we will have asphaltene?
Yes.
Okay, by using the SARA analysis. The SARA analysis, the main objective for the SARA analysis is for characterization of asphaltene problems. Okay, it will group the composition of the reservoir fluid into 4 groups. Like we mentioned into the slides, we have the asphaltene, we have the asphaltene, aromatics, resins, and saturates, but we have a simple method for knowing the amount of asphaltene into the reservoir fluid by adding light saturate hexane. Okay, so if we add just some of saturate hexane to the reservoir fluid, the asphaltene will be separated from the solution and deposited on the bottom of the cup.
Okay, thank you so much, Engineer Muhammad, for this interesting webinar. Of course, I will share again our PVT course link. If you can fill this link if you are interested in taking our PVT course, then you will know better, of course, about this topic. Thank you everyone for being with us today, and we'll see you in our next webinar hopefully. Goodbye everyone, and thank you, Engineer Muhammad, again.
Thank you.